Hi everyone, today we're going to be using our Raspberry Pi to build a simple calculator. We're going to get started by taking a look at our circuit connection. So we're going to need a Raspberry Pi, our breadboard, a 4x4 matrix memory and keyboard, which is the calculator, and an SSD OLED, which is just an LED made out of organic materials, as well as some wires to make the connections. We are going to be using this setup to detect the key feedback information of the 4x4 matrix memory and keyboard through the Raspberry Pi Pico. We're going to set the ABCD keys as addition, subtraction, multiplication, and division functions respectively to perform arithmetic operations and print the operation process and results on the OLED display to realize the function of a simple calculator. So on the screen I have the mappings for where the wires should be placed on the breadboard, but I also want to talk a little bit more about the 4x4 matrix memory and keyboard. So it consists of 4 parts: a panel, an upper circuit, an isolation layer, and a lower circuit. When the panel is not pressed down, the upper and lower contacts are disconnected, and the isolation layer plays an isolation role on the upper and lower lines. However, when the panel is pressed, the contact of the upper circuit deforms downward and remerges with the lower circuit to make the circuit turn on, and the level signal changes. When the finger is released, the upper circuit contact bounces back, the circuit is disconnected, and the level signal is in its initial state. I'm going to show both images once again to make sure that everyone has the correct configuration. Before we get started and open up Thonny, we need to download a library file to the Raspberry Pi Pico. So for this, we're going to open up Google and search for the library, which is ssd1306.py. We can find that on GitHub and copy and paste that directly into a new file right in Thonny. We want to make sure our Raspberry Pi Pico is connected to Thonny so that we're able to save this file directly onto the Pico. So this library file is necessary in order to use our SSD OLED. Now that our setup is complete, we can open up a new file and get started coding to make the calculator function. As always, we will start off by importing the necessary packages for the code today. So we'll start off with importing pin, timer, and I2C from machine, as well as utime and the SSD 1306 from the file that we just saved, as well as frame buff. We'll talk about these all more as we use them later on in the code. Next, we'll create a variable debug to use later on as a flag whether or not to print. Next, we're going to talk about I2C, which is a 2-wire serial communication protocol using a serial data line and a serial clock line. To initialize the I2C communication, we create an I2C object with the ID 0, and we specify that pin 21 will be used for the serial clock line, or SCL, and pin 20 for the serial data line, SDA. The frequency parameter sets the I2C clock frequency to 40,000 Hz. The next line creates an SSD 1306 I2C object named OLED. We're setting it up to control an OLED display with a resolution of 128 by 64 pixels, and we pass in the I2C object we just configured so the OLED object knows how to communicate with the display. Now let's set up the keypad. So the key name array is a 2D list that stores the characters that each button on the 4x4 keypad represents. Each inner list corresponds to a row, and the elements within each inner list are the column values. The keypad row pins array is a list that stores the pin numbers on the Raspberry Pi that are connected to the rows of the keypad. The next variable is keypad call pins. This list stores the pin numbers connected to the columns of the keypad. Next, we will initialize several empty lists, the first being row to store pin objects representing the keypad rows, call to store pin objects representing the keypad columns, and keypad state to store the state of each key in the keypad, pressed or not pressed. Next, we'll use a for loop to iterate through the keypad row pins list. For each pin number, it creates a pin object, sets it as an input, pin.in, and enables the internal pull-up resistor, pin.pullup. The keypad state list is populated with the initial states 0 for each key. We will create another for loop to iterate through the keypad call pins list. For each pin number, it creates a pin object and sets it as an output, pin out. Next, we have the functions responsible for performing the calculations. The first function will be solve. This function takes an operator, OPRT, and two operands, OPRDA and OPRDB, as input, and performs the corresponding arithmetic operation. It uses if and else if statements to determine which operation to perform based on the operator. The next function is calc. This is the core calculation function. It takes a list of operands and operators as input and evaluates the expression. Operand initializes an empty list to store operands, and operator initializes an empty list to store operators. The for loop iterates through the input list. If the element is an operator, it handles the operator precedence using a while loop to ensure operations are performed in the correct order. If the element is a parentheses, it pushes it to the operator stack or calculates until matching open parentheses. Otherwise, the element is assumed to be an operand and is appended to the operand list. The while loop after the main for loop handles any remaining operators in the operator list. Finally, it returns the result of the calculation, which will be the single element left in the operand list. Now, let's look at the function that reads the keypad input. Keypad read reads the state of the keypad and returns the pressed key. It iterates through each column, setting it to low, call i.low one at a time. It introduces a small delay using utime.sleep 0.005 for debouncing. It then iterates through each row, checking if the corresponding pin is low. If it is, it means the button at the intersection of that row and current column is pressed. It also checks for changes in the keypad state using keypad state to detect key presses and releases. If a key is pressed, it returns the corresponding character from the key name list. If no key is pressed, it returns -1. The next function handles displaying text on the OLED screen. Print OLED takes a list as input and displays it on the OLED screen. OLED position x0, y0 initializes a dictionary to store the current position for writing on the OLED display. OLED.fill0 clears the display, and string equals the empty string for I in list, string plus string I converts the list elements to string and concatenates them. The while loop handles displaying the string, taking care of line wrapping if the string is longer than the display width. OLED.show updates the OLED display with the content. Finally, we have the main loop of the program, but first we need to initialize some variables before we write that code. if name equals main line ensures that the code inside this block is only executed when the script is run directly. The while true is the main program loop which runs indefinitely. True is always true. Key equals keypad read calls the keypad read function to check for key presses. The next line, if key does not equal -1, means that if a key is pressed, for instance, keypad read returns a value other than -1, the code inside this block is executed. The code then processes the pressed key. If the key is a digit or a decimal point, it's appended to the current input. If the key is an operator, plus, minus, multiply, divide, it's handled based on the current input and operator precedence. If the key is S, it toggles shift mode. If the key is A or B, it handles the parentheses or pi accordingly. the key is C, it clears the input or the whole expression. If the key is equals, the calc function is called to evaluate the expression and the result is displayed on the OLED. Finally, print OLED input list calls the print OLED function to display the current input or the result on the OLED, and print input list prints the current input or the result to the console for debugging. And that's it. This code combines hardware control, keypad input handling, mathematical calculations, and OLED display output to create a functional calculator.